Well, thank you very much. It's a pleasure to be here in Lumini again, and thanks to the organizers for the opportunity to give a talk. I'm going to tell you about some joint work with a number of people. We have 3 different papers with those people here. Philip is here. And it was a very nice collaboration between Bonn and New York for part of this work. What I want to tell you about is what I think of as a kind of new subject that's emerging about the hierarchy of theories between Gödel-Bernays set theory and Kelley-Morse set theory. What's happening is that there are many natural principles of second-order set theory turn out to be equivalent to each other over that base theory of GBC, and it's very reminiscent of the situation in reverse mathematics of second-order arithmetic. And so I call the subject the reverse mathematics of second-order set theory. So what I want to do is show you some examples of what I'm talking about. So let's just first remember what Gödel-Bernays and Kelley-Morse set theory are. So these are second-order set theories, so they're axiomatized in a two-sorted language. We have the first-order part, which consists of the sets, and both of these theories assert ZFC for the set part. And then, in addition, we have a number of classes, a family of classes, which are subsets of the first-order part. We have all the usual axioms that you might expect, and the difference between GBC and KM is that Gödel-Bernays has the class comprehension axiom, the assertion that this is a class, only for first-order formulas phi with finitely many class parameters. So all the quantifiers are just first-order quantifiers in the GBC case, but Kelley-Morse allows this comprehension axiom for second-order formulas, so you can quantify over the family of classes in order to define new classes. So that's the main difference. Both of them have the global choice principle. Recent work, this is the work I'm talking about, places these natural second-order principles between these theories or slightly beyond them. And I'd like to tell you about these 3 examples: the class forcing theorem, determinacy for clopen class games, and the class choice principle. So those are the 3 parts of the talk here. And I'd like to tell you how that works. So this is a picture of part of the hierarchy of second-order theories. So we have Gödel-Bernays at the bottom. I'm sorry, maybe this is too small to see. So at the bottom we have GBC, and then consistency assertions or iterated consistency assertions. ETR omega is getting into the elementary transfinite recursion hierarchy for recursions of length omega. That implies the iterated consistency assertions. And then we have sort of higher fragments of ETR. This big bubble here is the class forcing theorem, which turns out to be equivalent to a number of different statements, including ETROrd, which is the assertion that you can carry out class recursions of length ord. Then if full ETR, which allows class recursions of arbitrary class, well order, or length, going beyond ord, is equivalent to clopen determinacy. For class games, open determinacy is strictly stronger. And then you get into the second-order fragments of comprehension that lead up to KM, and class choice is strictly stronger, not provable in KM. And then there's these fragments at the top. So this picture is linear, of course, but the hierarchy we know is not linear. For example, delta 1-1 comprehension is incomparable with ETR, and there are other instances of nonlinearity that I didn't show.
What is the base theory you proved?
GBC. So we're using GBC as the base theory. Gödel-Bernays. Okay. So all of those theories that I just showed have very low large cardinal consistency strength, because if kappa is inaccessible, then V kappa, together with all of its subsets, is a model of all of the theories. So the large cardinal strength is very low, but there's a sense in which the hierarchy is kind of orthogonal to the large cardinal consistency strength hierarchy, because you can ramp up the strength of the first order part, and the second order hierarchy remains exactly the same. So if you work over GBC, or if you work over a base theory of GBC plus a proper class of wooden cardinals or supercompact cardinals, whatever you like, then the picture of the hierarchy is still the same. So there's basically 2 ways to make your theory stronger. You can strengthen the first order part by adding, say, large cardinal axioms to the theory, or you can strengthen the second order part in the manner of the hierarchy that I'm describing. So this, a different kind of hierarchy of strength than the usual large cardinal consistency strength hierarchy. Okay, there's this backbone to the hierarchy that I mentioned, the ETR assertions. So let me just explain what that is. The principle of elementary transfinite recursion says that if you have a first order formula phi and you have a class well order, so this is a well ordered relation on some possibly proper class, maybe on the ordinals. So the order type could be much longer than ord, maybe it's ord to the omega or ord squared or whatever you like. Then a solution to that recursion is a class, a two-dimensional class whose sections are defined by that formula over the previous part of the recursion. So the alpha slice, where alpha is something in the well order, is simply the class of all x that satisfy the formula relative to the previous part of the solution at coordinates beta preceding alpha. So this is just iterating the phi to define a proper class sequence of sections of length gamma. Okay, so the ETR principle is of course stratified by these ETR gamma assertions. As gamma gets longer and longer, then you get more and more strength from the ETR assertions. ETR omega already implies that there's a truth predicate because of course to define the Tarski recursion, the Tarski definition of truth is a recursion of length omega on the formulas, right? You define the truth of a formula in terms of the truth of the previous formulas. That is a kind of recursion of exactly this type. ETROrd says that every class recursion of length ord has a solution, and maybe that's a little bit easier to think about. So you have the solution is a subclass of ord cross v, and the alpha slice is defined by phi relative to the previous slices. Okay, so let me tell you now about the first instance of this kind of reversal of the class forcing theorem. So consider a class forcing notion P, a partial order, separative partial order. Perhaps it has a forcing relation. We're interested in the assertion that every such class forcing notion has a forcing relation. And the goal is to analyze the strength of the class forcing theorem. What is the reverse mathematical strength of that assertion? And the answer, this is this collaboration between Bonn and New York. The class forcing theorem is exactly equivalent to the principle ETROrd over the base theory GBC. Now, we should clarify exactly what this theorem means. I'm claiming we've proved this theorem in GBC, and so in particular, well, this statement I just defined for you, that's assertable in the language of second order set theory, but maybe this statement is a little less clear exactly what it means in terms of a statement in the language of second order set theory. So let me clarify that. Exactly what is this statement? What does it mean? The usual way, I mean, it's quite common to give a kind of model theoretic account of class forcing relations. So you have a model of set theory, and you have a forcing notion, and then you define externally to the model the forcing relation. You say that P forces phi if whenever you put that condition into a generic filter, then the generic extension satisfies phi. And that's totally fine, and this is quite a productive way of defining the forcing notion if what you want to do is use forcing to build models and prove consistency results or something like that. But this kind of way of defining the forcing relation is problematic for the problem of finding the reverse mathematical strength because it's not asserted in the right language. This is not a statement inside M. So this definition takes place in the meta theory, and even if the forcing relation is a class in M, it's not so clear at first maybe whether M can know that. Can it recognize its forcing relations? And also it doesn't work with uncountable models or in situations where there aren't any M generic filters, because then this is vacuous. If there aren't any G, then this definition doesn't work. Okay, so what we really want is an internal account of the forcing relation that makes sense inside a model of GBC. Okay. You can get such an internal account if you just use the forcing relation recursion, the familiar one that you all learned maybe when you first developed the theory of forcing. So a forcing notion admits an atomic forcing relation if there are these relations on the relating conditions to atomic formulas that obeys this forcing relation recursion. This is, I think, the familiar recursion that probably most of you know. So a condition forces one name as an element of another name if densely often there's an element of the second name. and the stronger condition forcing that sigma is equal to that condition. Yes?
Are the names for sets? Or?
Names are sets, yes. So this is a forcing relation on the sets. Yes? So these are set P names, and what does it mean to have a forcing relation on the atomic formulas? It means to have a solution of this recursion. And that is a statement in the language of second order set theory. Okay, so of course you don't really need subset, that's just a convenience because you can define it from the other one. So you can view the recursion as really just on this one and this one. But it makes more sense to define the recursion using this subset. It's a little simpler. Okay, so, and then what does it mean to have a forcing relation on some other formula, phi? Well, it means that you have a relation that obeys the forcing relation recursion on phi and the substitution instances of its subformulas. So a forcing relation on a formula is defined on some set of formulas closed under subformula and substitution of names, and it obeys the atomic forcing relation that I just described, and it obeys the usual, the expected recursion. So a condition P forces a conjunction if it forces both of them, and the negation if there's no stronger condition forcing the opposite, and it forces a universal if it forces every instance of that formula. Okay, so the point is that to have a forcing relation is to have a solution of the forcing relation recursion, and that's entirely internal, and it can be defined without any reference to generic filters or forcing extensions at all. It's something like the definition of a truth predicate, if you know. It's just, the Tarski recursion is a similar way. Yes?
So phi is the first order?
Yes, first order here, yes. Yeah. So there's no problem with extending to the second order. The corresponding recursion would just, you'd have to define it. I mean, one can write down similar recursions for the second order.
You could have class parameters?
Yes, yes. Yeah, I omitted the class parameters here, so I'm simplifying a little bit. So one should have class name parameters here in the case of GBC, and in Kelley-Morse you really want full second order. Okay. So then once you have that solution of the recursion, you view the other assertions about the forcing relation as consequences. Namely, if you have a forcing relation satisfying that recursion and you happen to have an M generic filter, then it follows as a theorem that the force statements are true. So if P is in the filter and it forces a formula, then the extension satisfies V. And true statements are forced. If something is true in the extension, then there's some condition forcing it. You can just prove this by induction on formulas. It's a consequence of the existence of the forcing relation rather than the definition. Okay, so let me explain how the principle ETROrd implies that there are forcing relations for every class forcing notion. And that's rather easy. It's just because the forcing relation recursion is set-like. I'm sorry, in set forcing, the forcing relation recursion is set-like and has a solution in ZFC. That's how we know in ZFC forcing, when you're forcing with a set poset, that there is a forcing relation. You define that recursion and it has a solution because it's set-like, and in ZFC, set-like recursions have solutions. But in class forcing, that recursion is no longer set-like, and so you cannot necessarily prove that there is a solution in GBC. But with ETROrd, you can. ETROrd says exactly that you can carry out recursions of length ord, and that recursion is a recursion of length ord, and so therefore there's a solution of the forcing recursion. But it implies more, namely, not only is there a solution of the recursion, but there's a uniform solution. There's a single forcing relation that applies to all formulas at once with a single relation. And this is a stronger situation than we usually have in ZFC. In ZFC, we're used to having only a scheme of forcing relations. I mean, people say the forcing relation is definable, but they don't ever really mean that. What you really mean is that for every formula, there's a forcing relation for that formula. And you have to have it only as a scheme. But in ETROrd, we can have one forcing relation that handles all formulas at once. And so it's a kind of stronger situation than we are used to in the ZFC case. Okay, so I've explained how from ETROrd we can construct forcing relations. And the very surprising thing is that we can reverse this. So if every class forcing notion has atomic forcing relations, even only atomic ones, then we can recover ETROrd. So actually, there's a long list of equivalent statements. So this is just some of them. So statement 1 says, so the following are equivalent. The existence of atomic forcing relations, or the existence of a scheme of forcing relations, or the existence of a uniform forcing relation, or even a uniform forcing relation in the infinitary language, and you can define what that means. There's a certain infinitary recursion that probably you can reproduce. All of those are equivalent to the assertion that every P has a name for a truth predicate. And basically, one should think of a forcing relation as a name of a truth predicate. That's what it really is. So it's equivalent to the assertion that every separable class partial order has a Boolean completion. I mean a set complete Boolean completion. So there's a set complete class Boolean algebra into which the poset embeds. It's equivalent to a certain class join separation principle. It's also equivalent to the existence of truth predicates in the infinitary language, where you can take arbitrary set conjunctions. It's also equivalent to the existence of truth predicates in this full infinitary language, where you can also have arbitrarily large blocks of quantifiers. It's equivalent to the existence of an ORD iterated truth predicate in first order logic with class parameters. It's also equivalent to the determinacy of clopen class games whose game tree has rank at most ORD plus 1. And it's equivalent, finally, to the principle ETROrd. This is the implication diagram that we used to prove these equivalences. And so, so you can see statement 12 is kind of central here. That's the ETROrd, and it implies everything. 1, 2, 3, and 4 were the forcing relations. So this was the uniform infinitary one. That's the uniform first order one. This is the scheme first order one. And this was the atomic forcing relation. So those implications are all very easy. The blue ones are easy. The red ones are much more substantial. Basically, ETROrd implies all of them by just pretty easy recursions. And the substantial part is really getting back to ETROrd from those other assertions. So I'd like to tell you a little bit about how that goes. It proceeds in several steps, and there's these tricky syntactic translations into the infinitary languages that we do in order to turn the forcing relation into these truth predicates and iterated truth predicates in order to recover ETROrd. The first thing to notice is that if you have a forcing relation for atomic formulas, then you can easily get the scheme version just by induction. This is the usual induction, because that after you have the atomic forcing relation, then for any particular formula, it's just an easy recursion that you can do in GBC without any ETR assertion. Okay. So let me explain how to go from the atomic forcing relation to a uniform forcing relation in the quantifier-free infinitary language. So this means you can take arbitrary conjunctions, but you don't have any quantifiers. So quantifier-free infinitary forcing language, we can have a uniform forcing relation. And this is a construction due to the bond group. And the way it proceeds is to every infinitary phi in this language, you assign certain names, A dot and B dot. Yes?
Is this L sub or 0, is it the same as is sometimes called L infinity omega?
Probably. I'm not sure what you would mean by that. But I mean, arbitrary. The 0 means quantifier free. The 0 means quantifier free. Okay. Right. This. Right. So arbitrary conjunctions and disjunctions and negations, and that's it. Okay. So you assign these names, set names, to the formula, and the way I think about it is basically these names in the hierarchical structure of the names is kind of copying the logical complexity of the formula in such a way that. We're going to define now P forces phi if and only if P forces that those names are equal. So we design these names very carefully, precisely so that this relation, we have a forcing relation on the atomic formula, so we can tell when P forces two names are equal, and we define those names in a very particular way, precisely so that this definition satisfies the forcing recursion relation. I'm sorry, the forcing relation recursion. Okay, so that's all I want to say about that. Now, the next kind of translation step is that if you have forcing relations for atomic formulas for all class forcing, then there's a truth predicate on this infinitary language. And this step uses this special forcing F, which is the collapse of the universe to omega. Of course, this is not going to preserve ZFC or anything. It's collapsing V. It's sort of worse than the Levy collapse. Not only are we collapsing every cardinal, we're collapsing the entire universe to omega. So we're adding a bijection from omega to V, and then we add in these extra conditions here, which are supremums of certain antichains, namely E and M is above a condition F if f of n is an element of f of m.
Well,
Yes?
Again, sorry that I asked this. Is this L or omega? Is this what is sometimes called L infinity omega?
I think so, yes. I mean, I'm not sure exactly what you mean by that, but probably you mean the same thing. So, I mean, there's infinitary conjunctions and disjunctions and finite blocks of quantifiers.
It's like, okay, never mind.
Okay. Since we have global choice, it doesn't matter the distinction. We can well order the conjunctions and so on. That's no issue, if that's what you're worried about. So, because we're working over GBC, we have global choice. There's a global well order, so we can well order everything. Okay, so there's one thing to notice. This collapse forcing is, of course, dense in F, because we added these new conditions only on top of certain other things. And if you're used to the set forcing situation, then you might say, well, why would you ever add new conditions on top of other conditions, because that's going to be forcing equivalent. But the thing to know about class forcing is that this is not true. If you have a dense subclass of a class forcing notion, it's not necessarily forcing equivalent to the original class. The generic filters are going to be exactly the same, but the class of names are not the same, because with these new conditions, you can build new names that you weren't necessarily able to build without those new conditions, precisely because this is a proper class anti-chain. So this condition ENM is now one condition that is saying, I don't know anything about what the collapse function is doing, but whatever it's doing, f of n is going to be an element of f of m. And that's something that you can't say with a set number of conditions just from the collapse. So we add those conditions because we want to make reference to that concept. And so, so this forcing is a little bit different than just the collapse forcing itself.
Sorry, Joe, but
Yes?
generic meets
All dense classes.
dense classes, whether they're definable or not. All.
Just the classes that are in the model. Yes, there might be second order definable classes, and you don't have to meet those officially in order to be generic. Right. But in Kelley-Morse, those are all there anyway. So, okay. So using this ENM, you can define a certain name. It's a countable name, in fact, epsilon dot. And the generic collapse function is going to give you a bijection, I mean an isomorphism between the old universe and this relation on omega. So you use this condition ENM precisely to say when n is epsilon related to m. Okay, so now if we assume that that forcing has atomic forcing relations, then the claim is that we get a forcing relation on ETROrd 0. And that proceeds by this translation, the star translation. So for every formula in that infinitary language, we translate it to an assertion in the quantifier-free infinitary language like this. So epsilon turns into this var epsilon. So basically what we're going to try to do is truth in V is going to be the same as truth in this countable structure in the forcing extension. But this equivalence by itself is problematic, because if you do the forcing, then you can make this structure, but what you did is destroyed everything by collapsing the universe, and so you don't have ZFC anymore, you don't have anything, basically. You don't have a satisfaction predicate here, so it's kind of difficult to say what this is exactly, even in which model it's taking place. So you take this kind of equivalence as a metaphor, and you make this translation, the star translation, which turns epsilon into var epsilon, and the key step is this one, namely that universal quantifiers now just turn into countable conjunctions because the universal quantifier over here is going to turn into a certain statement that every natural number has the property over here, and that's why this translation is exactly like that. And so then if you look at the relation that one forces phi star, which is a quantifier-free infinitary assertion, because we don't have any quantifiers over here, and so we have the forcing relation for the quantifier-free one, so we define this, we get a truth predicate on V. I'm sorry, this should say truth predicate, not, no, I'm sorry, where are we going? We're building a truth predicate on V, that's the goal. I think what I wrote here isn't what I meant, but what I wrote here is what I meant. Okay, so now if you have a truth predicate on the infinitary language, then it turns out you can make an iterated truth predicate for first order truth. So this is another translation that we define. So, so what is an ORD iterated first order truth predicate? Well, that's where you have a truth predicate on the first order formulas, and then you have a truth predicate about truth, and then a truth predicate about truth, and so on, iterated, ORed many times. So we have a single truth predicate relation, and truth assertions are made at a stage. So we say such a statement in that language of the iterated truth predicate is true at beta if, okay, there's a certain recursion. What that means, the Tarski recursion for iterated truth predicates, and that's what we want to build here. So we make a translation from the stage beta truth of phi, where phi is a statement in the language of the ORed iterated truth predicate. We make another statement, phi star of beta, in the infinitary language. And by making that translation, we can produce the ORed iterated truth predicate. Okay, so finally, it's a theorem of Fujimoto, Kentaro Fujimoto, that ORed iterated truth predicates are equivalent to ETR. And if you look at that proof, then it turns into a proof that ORed iterated truth predicates are equivalent to ETROrd. And the basic idea is that if you have an ORed iterated truth predicate, then you can prove that any ORed transfinite recursion instance has a solution by extracting from the truth predicate what you need to do at each stage. Okay, so the final summary of the situation is that ETROrd gives you the atomic forcing relations and therefore all the other forcing relations. And from the forcing relations for that particular forcing, we can recover ETROrd via this multi-step translation process. Now, it's very surprising to me that it follows from the theorem that if every class forcing notion has atomic forcing relations, which seems like a kind of wimpy statement at first, it follows that they all have fully uniform forcing relations even in the infinitary language, because that's a consequence of ETROrd. And so just from having atomic forcing relations for every class forcing notion, it follows that you have these fully uniform ones, which is something that we're not really used to in the ZFC case, but in the GBC case, this is what you get. Okay, so let me now move on to the next instance of a reversal, and this is the proper class games. Yes? Sure.
I think there's a confusion here, because when you talk about the class forcing theorem, you're talking about it in the context of Kunin names, right? So all the complexity in the forcing relation lies in the atomic case, as you put it.
Yes, yes.
Because of the ranks involved in Kunin names.
Right.
But the fact is, you could do forcing with simpler names, with names of low rank, and get the same generic extensions, and then the class forcing theorem is provable in Gödel-Bernays.
For all class P,
Yeah.
or? Oh, I see. I want to talk to you more about that.
I think the confusion here, you're not really analyzing the class forcing theorem. You're analyzing the class forcing theorem via Kunin names.
Right,
And
except...
that's what's jacking up, and that's the whole theory of pretameness, was to pull that down for
I see.
ZF.
Okay, that might be true. I need to learn more about
There's
this.
this kind of variable there, and in fact, if you just drop the names, you say, I want a relation definable that defines forcing for sigma n sentences. That's provable in Gödel-Bernays. The complexity here is that you're sticking in these Kunin names.
Right, but that's something...
That's not going to be first order.
But you're describing the Kunin names like somehow that's totally weird, but this is the normal way that set theorists are understanding forcing. I mean.
I'm older than you, so I'm
okay.
before Kunin names.
Okay, I see.
But actually, it was in Bonn, so thinking the Cook about 20 years ago.
Oh, I see.
I had this conversation. I mean, at that point, he was obsessed with the idea that set theory is about sets of ordinals.
Right. Yeah, he has this theory, SO.
If
right?
you push on that idea, You can just, your names can just be basically names for sets of ordinals, pairs consisting of
Right.
continuous
Right.
ordinal,
Right.
And these names are very low rank, and then the force
Right.
relation in the atomic case is provably definable.
Right.
And then you avoid this whole business. So actually, the pretense was not to get the definability of forcing; it was reserved the replacements.
Okay. Well, that's very interesting. I mean, in another sense, for example, in the case of reverse mathematics, one doesn't say, well, look, you can avoid the complexity of a certain theorem by doing it differently and therefore bring down. I mean, the point of the reverse mathematics is to analyze what is the complexity of a certain statement. And so we've analyzed the complexity of the class forcing theorem as we stated it, and it's equivalent to ETROrd.
By the class forcing
Right.
theorem. This is a particular version of the
Sure.
class forcing.
So my
Other
expectation,
versions that are provable.
right, okay. So I think that's totally fine. I want to talk to you more about that. Okay, so let's go on to the proper class games. So the situation here is consider a two-player games of perfect information on a class. So the games have length omega, just like the games you all know about. But now the plays are coming from this class. Maybe they're ordinals. And player one wins if the resulting play is in some fixed payoff class. It might be a proper class. But the concepts of open game, strategy, and so on, winning strategy, all of these are expressible in the language of second order set theory. A strategy now is a proper class function from the finite plays to what the move is to be made in that game. Okay, so the situation, just to jump right to it, is that there's a definable clopen proper class game whose determinacy, so it's clopen. But if it's determined, that's equivalent to the existence of a truth predicate for first order truth. So in particular, you can't prove clopen determinacy in GBC because you would be proving the consistency of GBC. So in particular, also in ZFC, there's a definable clopen game with no definable winning strategy for either player. So clopen determinacy has strength. It implies con ZFC because the existence of a truth predicate implies con ZFC and iterated consistency and so on. Okay, so what is this game? I call it the truth-telling game. So there's two players. There's the truth teller and the interrogator, and I imagine them in a court of law, and the truth teller is sitting in the witness box answering the tricky questions posed by the opposing counsel, the interrogator. And at each turn, the interrogator says, is phi of A true? And the truth teller has to say yes or no, that it's true or that it's false. And there's a proviso here that if the assertion is an existential assertion and the truth teller says that it's true, then the truth teller must also provide a witness, a B, and assert that this is also true. Okay, so a play of the game consists of a countable sequence of those questions and truth assertions about those questions. And the truth teller wins as long as she never violates the Tarski recursion. So if she says that two statements are true, she must also say, if asked, that the conjunction is true. And if she says that a statement is false and she's asked about the negation, she must say that one's true. And she has to obey the quantifier. So if she says that phi of B is true, then she must say that there is an X, phi of X is true. Okay, that's an open game for the interrogator because if the truth teller loses, it's because she violated the Tarski recursion at some stage, and that happens at a finite stage. So that's an open game. And the truth teller has a winning strategy if and only if there's a truth predicate. So, of course, if there is a truth predicate, if we have a class which obeys the Tarski recursion, then the truth teller can simply consult that class and answer according to that class. And so that will be a winning strategy because she'll never violate the Tarski recursion because the truth predicate obeys the Tarski recursion. Conversely, if the truth teller has a winning strategy, then I claim that the truth pronouncements made by that winning strategy are independent of the order in which the interrogator asks the questions. All the truth assertions will be always the same. And you can prove that by induction on formulas. And it follows then that the truth pronouncements made by that winning strategy will obey the Tarski recursion and therefore be a truth predicate. Okay, so that shows immediately now that there cannot be a definable winning strategy for the truth teller. We don't yet have the theorem because maybe the interrogator wins. So this just shows if the truth teller wins, then it's because there's a truth predicate. But I claim the interrogator cannot win. So the reason is that if you have a strategy for the interrogator, so that's a strategy, it tells the interrogator which questions to ask. So there must be some theta which is closed under the strategy in the sense that no matter which answers or witnesses are provided, they always will stay inside v theta. But in that case, we can have the truth teller answer with the truth predicate of v theta. This is a set structure, therefore in CFC it has a truth predicate, and the truth teller can just answer, instead of about truth in v, can answer about truth in this v theta, which is this set structure. And that will defeat the strategy because the strategy is closed, v theta is closed under the strategy, and it does obey the Tarski recursion for that structure. Okay, so therefore the interrogator cannot win, and if the truth teller wins, there's a truth predicate. Okay, so open determinacy implies that there's a truth predicate. You can modify that game by, so that was an open game and not a clopen game, but the claim was about clopen games, but it's easy to fix by just requiring that the interrogator counts down in the ordinal. So on the first move you have to announce an ordinal, and then every subsequent move it has to be a smaller ordinal, and so on. This makes it a clopen game. So when the clock runs out, the interrogator loses regardless of whether the truth teller has succeeded so far. And then you can prove that, that now the truth assertions made by the winning strategy for the truth teller are invariant under the play, provided that the clock is high enough. So for sufficiently large clock numbers. And that again gives you the truth predicate. Okay, so the conclusion is that if clopen determinacy holds, then there's a truth predicate for first order truth. So that gives you strength from clopen determinacy for class games. But the stronger principle is that in fact, clopen determinacy is exactly equivalent to ETR. So in particular, it's strictly stronger than the class forcing theorem, which was only ETRord. This is full ETR. And the equivalence of 2 and 3 was known already by Fujimoto, as I mentioned. So the new part here is that it's equivalent to clopen determinacy. And the way it goes is very similar to that truth-telling game I just told you about. Namely, if you have ETR, then you can prove the determinacy of clopen games just by the back propagation method. And that's the usual proof of clopen determinacy, and you can undertake that proof in ETR. And conversely, if you have clopen determinacy, then instead of playing the truth-telling game, you play what I call the counting down recursion game, where the truth teller is now also giving pronouncements about the solution, the nature of the solution of the recursion. So you set up the recursion, and the interrogator asks questions not just about what's true, but also what's true about the solution, the supposed solution. And as long as the truth teller can obey the Tarski recursion and the definition of the recursion, then she wins. And so if she has a winning strategy, then there will actually be a solution of the recursion. Okay, so there's of course a very strong analog here with a result of John Steele from his dissertation. Namely, he proved that open determinacy and clopen determinacy for games on omega, I mean down low, are both equivalent to ATR0 and therefore to each other. But in second order set theory, we could only seem at first to get the clopen determinacy from ETR and not open determinacy, and so we couldn't prove that they were equivalent. We can prove open determinacy in stronger theories like KM, or actually GBC plus Π11-comprehension already gives you open determinacy for class games. And so it was open whether they were equivalent or not. And this was finally solved by Sherwood Hackman, who proved that they're not equivalent. So it's a departure from the arithmetic case. Open determinacy is strictly stronger than clopen determinacy for class games. And then there was also some work about this sort of Borel class game. So if you take the open games and close under, take the sigma algebra generated by those open games, then you get the notion of Borel class game. And KM does not prove Borel class determinacy. Okay, so let me move on now to the third one briefly, which is the class choice principle. Suppose for every natural number n you have a class x with a certain property, a first order property. Then does that mean that there must be a two-dimensional class whose sections have that property? So in other words, for every n you have a class, I want to put them together and have a single class. Okay. So that's the class omega choice principle. We're making omega many class choices and putting them together. More generally, the class choice principle says if for every set A there's a class with a certain property, then there's a two-dimensional class whose sections have that property. So we can choose for every set a class and put them together. So this principle is used in many natural constructions, including the Walsh Theorem for ultrapowers of models of second-order arithmetic. So if you have an ultrafilter, say even on omega, and you have a model of Kelley-Morse, and you want to make an ultrapower, you do the ultrapower construction, then you're going to want this principle in order to prove the Walsh Theorem for the ultrapower. And so the question is, well, can you do it? And in particular, are the models of Kelley-Morse closed under the internal ultrapower construction? And the answer is that they are not. So you cannot prove this principle in KM, and the ultrapower of a KM model is not necessarily a model of KM. So there's some other failures that I proved with Victoria Gitman. So first of all, there's that ultrapower violation. And secondly, KM fails to prove that sigma 1,1. And by this I mean the class existential quantifier. I'm not talking about sigma 1,1 in descriptive set theory. This is the second order set theory version of sigma 1,1. It's not closed under first order quantifiers. Namely, if I put a first order quantifier in front and phi is sigma 1, then this might not be equivalent to a sigma 1,1 formula. And of course, to prove that equivalence, you want to be choosing for each x a class. So you can see how the class choice principle is coming in there. So there's some other things. We can make a model of KM which holds the omega choice principle, but I'm sorry, in which the omega choice principle fails. So even the omega choice principle is not provable in KM. We can make the set choice principle hold, but the ORD choice principle fail, so we can separate the difference between less than ORD and ORD choice. We can make the ORD choice hold, and the second order ORD choice scheme fail. So we can make these separations. And all of this is happening above KM. So if we go back to the hierarchy that I'm sorry you can't see, but this is KM, and then we make these separations above KM with various amounts of class choice. So let me close by asking a number of questions. There's really a huge number of questions in this area, and I invite all of you to start working on these questions because I think they're really quite interesting. So the first main question is to understand more deeply the interaction of the second order principles with forcing. So we don't know which second order principles in the hierarchy are preserved even by set forcing, even by adding a Cohen rule. There's some open questions about which principles are preserved. Of course, GBC and KM and KM plus and so on, these are preserved. But some other ones are not. And in particular, ETR, we don't know if it's preserved even by adding a Cohen rule. And the problem is, well, any instance ETR gamma for fixed gamma is preserved. We can prove that. But the problem is that we might create new order types, new class well orders that are taller than anything we had before. And we don't know how to handle this situation or to rule that out. Another question is the role of global choice. So maybe it's true that GBC plus ETR is conservative over the GB plus AC. So this one doesn't have, this one has global choice. This one only has the axiom of choice for sets, but no global well order. And of course, to prove that it's conservative, you would want to start in a model of this theory and then force global choice. But again, the problem is that maybe that creates new gammas, new big well orders that we don't necessarily have solutions for the recursions for. So another is the unrolling construction. So this is the process of unrolling a model of second order set theory to a much taller first order model. So just like reals can code hereditarily countable sets, you can have class relations code some extensional well-founded relation. They're coding some kind of superset on top of the universe. So if you take codes, say, class codes of well-founded extensional relations, then KM plus, that's with the class choice principle, is bi-interpretable with the theory ZFC minus I. So that's ZFC minus without power set, but plus the assertion that there's a largest cardinal which is inaccessible. So the old ordinals become an inaccessible cardinal in the unrolled structure. And the question is, so if you start with KM plus, then you get ZFC minus I, and conversely, if you have a model of ZFC minus I, then you can produce a model of KM plus with it.
What do you call it, KM plus?
KM plus class choice.
I.
So which second-order theories can implement that unrolling construction? It seems like even weak theories can do a lot of it, but to prove that the unrolled structure on top, the sort of universe that you build on top of the universe, has even some basic properties seems to require some strength in the theory. For example, even to get extensionality seems to use some delta 1-1 comprehension in the Bayes theory. And so we're not clear exactly if you have only ETR. ETR is enough to produce isomorphisms of things that should be isomorphic, which seems relevant to the unrolling construction, but we're just not sure how unrolling works with these weaker theories. The second order reflection principle is the assertion that every second order assertion is true in some coded class model. So if you have a class that is a two-dimensional class, you think of its sections as a family of classes, and you can take those classes and make a model of second-order set theory out of it. And the reflection principle is saying every second-order statement that's true in the universe is true in such a coded model. And we don't know what the reverse mathematical strength of that is. It's related to the question of whether CFC minus proves that every first-order statement reflects to a transitive set. Another question is the strength of well-order comparability.
That was answered by Gödel and myself.
It was?
Yeah.
Oh,
Our paper
in ZFC minus, you mean? Or this one? The strength?
Yeah.
What is the strength?
Oh, not the, no, the fact that you cannot prove this reflection is that of C minus. That
Oh, this one.
Reflects, yeah.
This one. Oh, I see. Oh, it's false.
It's false. Yeah.
Okay, thank you.
That's this paper of ours on AC design.
Okay, I want to look at that. Okay. Does it answer this one?
Oh, I can't remember. What does it say?
Can you turn it into a GBC example?
We think so, but it's hasn't been written down.
Okay. Okay, I definitely want to talk to you about it. Okay, so well-order comparability is the assertion that if you have two class well-orders, that one of them is isomorphic to an initial segment of the other. So ETR can prove this, but we don't know if it's equivalent to ETR or is it provable in a weaker theory. It seems like ETR is a very natural guess for that because the comparability assertion is just very naturally a transfinite recursion of that length. And so my guess is that it should be equivalent to ETR, but we don't have a proof of this. The class Fodor theorem. So that's the assertion that every regressive function on a stationary class is constant on a stationary, that should say class. Okay, you can prove that in KM plus, but it's not clear how to get rid of this class choice or what the strength of the assertion is at all. Then the stationary partition. So the assertion that every stationary class can be partitioned into disjoint stationary classes. So of course, in the strongest theories, you can run the analog of the classical arguments, but without class choice, and in the weaker theories, it's not clear at all what the strength of this assertion is in the second order context. And it seems to be related to stationary reflection. My student Corey Switzer and I are looking at what we call the class forcing axiom, which is the assertion that for every class forcing notion, meaning that we have forcing relations and we're not adding sets, then for any ORD sequence of dense classes, there's a filter meeting them. So it's like a class forcing version of Martin's axiom, but it's for distributive forcing, which is false at omega 1, because if you have disjoint stationary sets at omega 1, you could shoot clubs through them. You can't have filters for both of those. But in the class case, you can have it. It's consistent with GBC. And it has many interesting consequences. ORD is not Marlowe, no Suslin trees, diamond fails. Every fat stationary class has a club already. So that seems to be quite interesting. And also this principle, what we call the class forcing maximality principle, which is the assertion that anything that's possibly necessary is already true. And what do I mean? I mean for any statement phi of x, which is forcible by class forcing, which doesn't add sets, and which stays true in all further such extensions, is already true. So that principle implies the class forcing axiom, and also it's conservative over GBC. If I have a GBC model, I can make that true without adding any sets. And it's not clear exactly which models of second order set theory that construction works with, and also which of the second order theories are conservative for the first order assertions in that way. So we can make models of GBC plus ETR plus the maximality principle and therefore also the forcing axiom by starting with a model of Kelley-Morse and doing our construction. This is what we get. So these are the three papers. So this one is the clopen determinacy one and the class forcing and the KM plus paper. And thank you very much.